Okay. What do we do with Helmholtz resonators? We can use it as a muffler. It's a little bit different than what we have done before, but you can put it on the side of, let's say, a pipe, and write the equations of motion, or the acoustic field equations. And you can see again a sound wave that's coming. Now, there will be an impedance change here, right? Because there's another sound field inside the resonator. And some sound will be transmitted, some will be reflected. So let's write down the equations, sound pressure equations for this system, and see how a Helmholtz resonator can be used as a muffler. Okay, you can see now the left-hand side and the right-hand side are, as usual, in the same manner. But what we have, this is the interesting part here, okay, that you should notice. Pressure will be equal, but there's going to be a difference in the particle velocity flow. Okay, mass flow equation is going to be different. In some ways, we had to keep the time dependence because just Q has its own resonance. In some ways, incident and reflected, the particle velocity just immediately to the left, okay, times the area, and the transmitted on this side, particle velocity times the area, and the mass change. Remember, we talked about the mass flow in and out of the Helmholtz resonator was Q. So without Q, you can see we have S times I minus R, T times S. The usual expressions for continuity. Okay? And so now we say, no, the flow here, some of it goes in there and some of it goes into the pipe. So that's the balance. And from here, if we pull out the transmission expression for pressure, we now have an expression that also has the Helmholtz resonator's properties. And can you remember what's transmission loss? How would I write the transmission loss here? TL equals 10 log 1 over T squared. Absolute value. Very good, 10 log. Okay, so the transmission loss is inverse of this, 10 log. You can see the expression here. Please pay attention, this is negative minus 2, so it's 1 over square of that expression. We'll have probably some homework problems on these that will ask you to examine these parameters. How do you optimize them and so on, okay? And so you can see now that by selecting the length and the volume, we can actually modify the transmission loss in the system. So Helmholtz resonators are commonly used, by the way, for reducing the sound pressure, usually in hydraulic systems as well as normal pneumatic systems. Okay? All right. A different but related topic is transmission of sound into branches. Well, let me first start with this very simple concept about how the impedances are related, okay? One is, the first thing we do is write the expressions for a pressure field. Again, if I have just your attention for a second, here is where the sound comes from, and their impedance changes, and some is reflected back. So we call this 1, and this is branch 2. Cross-sectional area S1, S2, the particle velocity, sound pressure, P1U1, P2U2, and so on. So what we're saying is, at this point where they intersect in that little narrow region, pressures must all be the same. If you have a pressure differential, then you have acceleration of the fluid, and that's not physically possible. So pressures are all the same. Particle velocities have to show identity, and if you divide them respectively, you have the inverse impedance relationships. What does this remind you of? This sort of a inverse impedance relationship. You have seen this. At least for mechanical engineers, but electrical engineers. Parallel springs, or serial, no, in series. What's that? Parallel springs. You sure? Okay. Impedance is splitting into two, parallel. So, an impedance relationship. But when you have, when you have a branch like this, okay, and these are very common, and you have sound pressure propagating, but then there's another duct that takes off. It's no similar than the previous one, but basically we have a relationship between the areas and the particle velocity to all different branches, but the pressures must be the same. Okay, this is the key. And then we have the impedance relationships as we have just written before. These we have derived these all before, okay? Very similar to what we have done in the past.
Can you just go back to previous slide?
Sure. There's something that's bothering me about that too. The area.
And the last one.
This one?
Well, it's possible one of these is equal to.
Oh, it's not Z, this can't be. This is 1. Sorry. Can't be. Yeah, it's just this. U1 over P1. So I should go much faster. You're catching all my errors. Very good. have another question to myself here. Okay. These are expressions for reflection coefficients in terms of the branch impedances. It's the same, actually. This is capital, but it's the same B. Yeah. Okay. Let me solve the homework problem in the remainder of the time and see if we can help you in any case. I think I'm pretty much done with the duct problems. There are some other aspects that are important, but I'd like to move on to the plates, plate vibration and radiation from plates, transmission from plate structures, interaction of sounds and structures next time. And one more thing, then we'll cover that. Now, okay. Do you have any questions about what we presented so far? My suggestion is go back and review some of these and try to rederive them, okay? And if you have any questions, you're not here during the week, right? You can just send me email, no problem. If you have any questions, because these guys are able to come and knock on the door, they have questions, and they should feel free, you should feel free, just send an email, okay? Any questions on these? I'm going to turn this off and use the blackboard now, okay? The homework problem was a certain acoustic tile, and acoustic tiles are these things up here. They're called acoustic tiles. It has a normal specific acoustic impedance that's defined by a complex value, Pascal, second meter. Just please. Okay. Tough question, right? For what angle of incidence in air will the sound power reflection coefficient be minimal? And so they're asking what should be the incident angle that R pi should be minimal. That's one question, okay? Now, I think once you solve that, the rest will be easy to understand. So let's say here's the tile, and we have incident wave, reflected wave. By now we know that these are equal, but let's write the pressure field. Okay, these are the pressure field in front and behind the tile. Now, since we're interested in reflection, we get the particle velocity in front of it, and we can write that as now, we can show that incident and reflected angles are the same. Okay? So we'll take them to be the same. What I want to do now is write the impedance. Impedance expression for impedance expression at x equals 0. Okay, is that okay? And that is, let me just, that will be P1 U1 x equals 0, and that will be okay. Where you probably had a difficult time is what to do after this. Okay? What should you do after this? What it does is it gives you the properties of a surface, impedance properties, normal acoustic impedance. And the question is straightforward. So what would you do? What do you have to do now?
Actually, rather than deriving these equations, you have supplied us an equation in terms of normalized impedance, reflection coefficient. I use this equation, reflection coefficient, equation, but here the question is how am I going to use the complex impedance?
Exactly.
Do I need to use real part, or do I need to find magnitude of the impedance? I found the magnitude of the impedance on surface, and I substitute the value into the reflection coefficient equation.
Yeah.
And the rest is the
One thing that here's a hint that you should keep in mind. You have a surface that has an impedance that's described as a complex number. Okay? What that should suggest to you is the sound field probably needs to be expressed in complex terms also. Okay? And acoustic impedance, usually the types of boundary conditions we have used in the past, if you remember, we said either rigid surface, open, pressure is 0, or particle velocity is 0. But I also told you once that what happens if it is neither, something in between, then you use impedance. So here now, what you want to do is for continuity as a boundary condition, the normal acoustic impedance and impedance of the surface must be equal. So otherwise it will not be continuous. Okay? So that means you could say pressure on the surface divided by velocity on the surface, or you just say this. And this has, of course, a real part and an imaginary part. Okay? And you make sure that they're equal to one another. Let's continue with that and see where that takes us. Do you follow this so far? Does this make sense? Conceptually? Okay, there's no problem. you know what? Too many R's is going to make us, let me just make it a different, make it real, well, how shall I do this? Like a real and imaginary, because it's going to get confused with the reflection coefficient. So going back to the expression here for impedance. Oops, it should be 1 minus R. No, 1 plus R. You have a question? No? Yes? Oh, okay. Okay, so actually this, let me just take this as the normal impedance for the time being. What do I want to do here? Okay. Okay, now if you write in real and imaginary parts, I hope this is, yeah. Okay. What we did, okay, what we did is we wrote the equation right here. Pressure field dividing, you have the impedance at x0 at the surface. Okay? And then we say that must be equal to the impedance of the surface, because that's what causes the reflection, determines the reflection amplitude, and so on. And basically, you just solve it for R, okay? And you have an expression, R being the coefficient of reflection, okay? So you have an expression, complex expression, and we separate the real and imaginary parts. This is the coefficient of reflection for the pressure waves. Now the question is, the question was, what makes the power reflection coefficient minimum? What is the angle that makes it minimum? Well, what is the power reflection? Absolute value squared, right? So this would then give us So we're really asked what value of theta I will make this minimum. So you can take, you have to solve basically a quadratic equation, and that will, I'm missing something here though. What am I missing? I forgot to multiply something. Oh. No, that's fine. Same. You could write this a little bit differently, but this is fine. Yeah, you could also write this. Yeah, it makes no difference. It's the same idea. It helps you visually see minima and maxima a little bit better, but yes.
How come we took square of that one?
I'm sorry. How come we what?
Sorry.
Yeah.
From the last yes to that. We have square of the first, square of the second, and then 2 times.
2 times? No. That's the absolute value. This is the absolute value. You can have A plus IB x plus I, let's see, yes, x plus IY, the absolute value. Okay. Okay, so next thing we do is what's the value of cosine theta or theta I that makes it minimum? One thing you can quickly say is, okay, just a near minimum, okay? Near minimum is when okay, it's not minimum, but it's near minimum when you make the 0. And that gives you a very close answer. Otherwise, you can solve it numerically. This gives you 63 degrees, but the actual minimum is 73 degrees. Of course.
Rather than deriving all these equations, if I get the magnitude of the impedance of the surface,
Magnitude of the impedance of the surface.
and I substituted this value into the normalized impedance equation, to supply us R is equal to normalized impedance times cosine
What's normalized impedance?
zeta n divided by rho c times cosine incidence angle minus 1 divided, sorry, whole divided by.
Everything, oh yeah.
Cosine theta.
Okay.
And if I say that this is equal to 0, I will get the incidence angle is equal to 73 degrees, but I don't know. So
This is a reflection coefficient.
magnitude of square of the,
But this is reflection, right?
yes, I mean, square of them is, square of it is
is the power reflection coefficient. That's fine. You mean this?
Yes.
Okay.
And the minimum value of the power reflection coefficient should be equal to 0.
Okay, so what?
Setting that equal to 0.
Okay, so you put here the magnitude of that, like this.
And I got the same result.
73 degrees,
73
plus minus.
45.
Z. I'm trying to remember what that Z was. I want to say it's a coincidence, but let me take a look at it. Yeah, I want to say it's a coincidence because, yes, you know why? If you look at the impedance here, Zn 900 minus I 1200. Okay? Now, if you take its absolute value, it'll be 900 square plus 1200 square root. That's what you did, right? Okay. And that gave you that value, which is coincident with this. But if I turn this around and make this 1200, make this 900, so change these values. Now, I don't know that I would get the same value again. You see, this number would change, but that would not. It's worth checking. Because the absolute value is just their squares, but and there are lots of different combinations of these that will give you the same Zn. But that would not be necessarily correct in giving the right angle. You see what I mean? But I'll take a look at it just to make sure that we're doing the right thing. Any questions on this? See how it is done? Okay. And the next part, I think you probably can manage the others. What is the power for the angle of incidence? I think you can manage the others. Were there any problems with the first question? No? First question? No? Okay. Well, I'm glad. Okay. Okay. Any questions about anything? Nothing? Are you tired? Okay. All right. Well, let me see what I have. In the next class, I want to show you, I thought we would get to it today, but transmission matrix. This is a really, you don't have to take notes now, but it's a very simple, easy instrument to do calculations, okay? What it does is it uses a matrix concept, okay? And for example, between two places, x1 and x2, between two places you have pressure and particle velocity, pressure, particle velocity. The relationship between them, it's like a state equation, okay? Expressed as a matrix. So you have these matrices you can develop for a silencer, for a membrane, for a plate, etc. So to calculate the sound pressure, especially in a computer, all you have to do is put these matrices side by side, just the way that they're organized. It is really quite a remarkable system. And I don't think you will find these in the books. This was invented by Professor Ingard at MIT. And he had taught me this. I learned from him. It's really very, very helpful. So next time I will drive this, very straightforward, very simple, and then we'll learn it. And then, well, we have a little exam, but maybe, I don't know which one we should have first. First the exam, maybe? Okay, first the exam, and then cover these, and then we'll move on to plates. When a plate vibrates, how does it radiate sound, and how does sound go from one side to the other? We'll cover those and continue with our program. Thank you. See you next week.